So in the last lecture, we looked at the spectrum of the cosmic microwave background. Today, we'll start looking at the anisotropies. And in particular, we'll start looking at the anisotropies caused by our motion with respect to the cosmic microwave background. So we'll look at the kinematic dipole. And what we discussed in the last lecture was that in the CMB rest frame, the spectrum, or in this case, I'll work with the occupation numbers because they're Lorentz invariant. The occupation numbers, so let's say in the CMB rest frame, as a function of the photon momentum, is well described by the black body spectrum. So it's e to the p over kt minus 1. But we're unlikely to be in this rest frame. So this is, I think it's obvious, but it's just because the Earth moves around the Sun. The Sun moves in the galaxy. The galaxy moves in the local group moves, so you get the idea. So somehow we and the satellite we're making the measurements from should be moving. So it's very unlikely that we see this spectrum. So instead, the coordinates we usually set up should be related to the coordinates in the CMB rest frame by some Lorenz transformation. So let me just call the coordinates that we make the measurement from x mu for the solar system. Should be lambda mu nu x nu for the CMB frame. And then if we're moving in the x direction, with a speed v, the Lorenz transformation is just, as you know from your special relativity class, is just gamma v times gamma, where gamma is the usual 1 over the square root of 1 minus v squared. I'm setting c equals 1 now. Gamma 0, 0 with a minus sign here. 0, 0, so we're moving in the positive direction. 0, 1. And with this Lorentz transformation, then we also know that the momenta that we assign to a particle are related to the momenta assigned by someone in the CMB rest frame, again by the same Lorentz transformation. And we also know that the occupation number, so the occupation number is a Lorentz invariant quantity. It doesn't matter how fast you're moving, you're just maybe relabeling exactly what you're calling the different states. But if you have 5 photons with a given label, then there will still be those 5 photons around. So what you know is that the occupation number in the frame of the satellite or the solar system evaluated at the momentum that's assigned by the observer in that frame should be the same as the occupation number in the CMB frame at the momentum that's assigned to that set of photons in the CMB frame. And so since these are related by the Lorentz transformation, we also see that the occupation number in the solar system's frame is lambda, and we can drop the label. So this is lambda mu nu times, well, here I should have put CMB. and put the nu up. And so here we have lambda p CMB, which I can then I can drop the label. This is equal to the occupation number in the CMB frame evaluated at p. And what's even more helpful for us, because we're trying to just understand what's the occupation number for our labels, we can write this as the occupation number in the solar system, or in our frame, the frame of the satellite, as a function of p, is the occupation number in the CMB frame as function of lambda inverse p. And lambda inverse, obviously, lambda inverse is just the same, but with plus v. So this is the Lorenz transformation, and then we also know that the occupation numbers in the CMB frame only really depend on the energy or the zeroth component, so the only thing that we really need is lambda inverse p, the zero component. And so if you look at it in our example where we're moving along the x direction, so if you multiply this by p, then you get gamma times p plus v times px, or by rotational invariance in general, we just have lambda inverse p, the zero component is gamma times p plus v, and I forgot the gamma here, so there's the gamma from here, gamma times v times p, gamma times v dot p. Okay, and then with this occupation number, we can just plug it in. We now find that the occupation number that's seen in the frame of the satellite or the solar system of P is equal to 1 over, and then lambda inverse P0 is the thing we just computed. So this is gamma times P1 plus P hat, because I'm pulling out P dot V over KT minus 1. So this is the occupation number as seen by the observer that's moving with respect to the cosmic microwave velocity v. And for small velocities, which is what we'll be interested in, we can just set the gamma to 1. So this just becomes e to the p times 1 plus p hat dot v over kt minus 1. And so what we can do, so this is the CMB temperature, or the temperature that we assign to the cosmic microwave background in the CMB frame. So we can define an effective temperature in this frame as T in the solar system frame as a function of P hat is just T CMB divided by this gadget here, divided by 1 plus P hat dot V. It's just from reading off the contribution there. And so then usually we don't quote it as a function of the photon's momentum, but we quote it as a function of the direction. But if I'm looking in the direction n hat, then obviously the photons reach us with momentum minus n hat. So we have p hat is just equal minus n hat. And so what we find is that the temperature as a function of the position in the sky that we expect to see is T as a function of n hat is just the CMB temperature divided by 1 minus n hat dot v. And again, we can expand that out for small velocities as T CMB times 1 plus n hat dot v. It's a geometric series, so it's just n hat dot v squared plus dot dot dot. And so you see that this looks like a dipole. So the temperature is slightly higher in the direction you're moving and slightly cooler in the direction you're moving away from. This is what we would literally see if we at every point in the sky measure the spectrum and try to measure what the temperature is at that point. In practice, that isn't really what's done. If you look at what the satellites actually measure, they just measure different maps at different frequencies, so they don't take the spectrum at every given pixel. What they look at is the intensity of the radiation as a function of nu hat. This is again set by the black body spectrum, but so we should expand this for small temperature perturbations. And so then there's the monopole. This is the usual monopole. And then just in a Taylor series expansion, this is d of the intensity. Nu here, I'm just indicating the frequency which you're taking the map. So this might be 100 gigahertz, 353 gigahertz, whatever is your favorite frequency. And really for the satellites, it's a range of frequencies, but it doesn't so much matter. So this is just meant to indicate the intensity at a given frequency as a function of the position in the sky. So then there's the overall piece, and then we can expand for small perturbations. So it's di by dt evaluated where the temperature is equal to the CMB temperature times delta t. But delta t, so the perturbation in the temperature at this point is just T CMB times n hat dot v. And so you see that, again, you have a dipole in this map where it's slightly hotter in the direction you're moving and slightly cooler in the direction you're moving away from. And so this is something that people understood from the very beginning, something people started looking for basically as soon as the cosmic microwave background was detected. And so I'll show you some of the old experiments. I'm not starting with the first attempts. There were attempts before this paper, but I'm instead just starting with the first one that measured the right ascension, declination, and the amplitude. And this is a paper, as you can see, from 1971. The values of all of right ascension, declination, and the amplitude are still consistent with what we know today. And the reason I think this is fun is because you see it was done by a single person. And what makes it even more fun is that this was a grad student. So this was a single grad student who measured this, who built the instrument, launched it on a balloon, and then analyzed the data, included some model for the galactic mission, and so on, and got the right numbers. And interestingly, after that, he left the field. But anyway, so I guess he felt he was done, maybe, I'm not sure. So that's the first measurement of the dipole. And then the measurement that's usually, so here there's additional attempts at higher precision. This is usually the experiment that people associate with the measurement of the dipole. This is by Smoot and collaborators, and these were the detectors that were later flown on the Kobe spacecraft here on a spy plane. And here is just a history of the various measurements of the dipole. So you see there was attempts right after the discovery of the CMB, so it was understood that there should be some effect like this. and people looked for it. This is the measurement I just showed you by Paul Henry, and then this up here is the measurement by Smoot, and then eventually the precision got higher and higher, and this eventually ends at 96, but we also have high precision measurements from the Planck satellite. And in the beginning, I erased it now, but I was saying that the Earth moves around the Sun and the Sun moves, so both of those are detected, and in fact the maps are calibrated on what is called the orbital dipole, the motion of the Earth around the Sun, not actually the solar dipole. Okay, so this is the kinematic dipole, but you might ask, how do you actually know that this dipole is due to the motion of the satellite relative to the CMB? How do you know that there isn't some intrinsic fluctuation? And it's I think a good question, and in principle it's something one can also study. So the question is, how do we know And one of the hints you might get is that it's larger. So if you look at the amplitude, this is a 1 part in 10 to the 3 effect. All the other fluctuations we see that weren't discovered at the time yet are of order 10 to the minus 5. They're much smaller. So you would think that the dipole presumably should be of order the other fluctuations in the CMB. So that's one indication. But then there's better ways to go about it, because there are additional predictions, additional effects caused by the motion and, well, let me just squeeze them in here. So the first one that I'll discuss now is what is called as the kinematic quadrupole. It's kind of obvious what that's supposed to be. I mean, you saw that we truncated this expansion here, so there's additional effects. And then, so far here we're only taking into account the monopole of the CMB and the effect of the motion on the monopole, but there are also effects on the anisotropies. So there's aberration, and modulation of the CMB anisotropies. And so let's look at how these things work. So the first one is the kinematic quadrupole. And so here, remember, so the temperature is still there. So we know that the temperature in the solar system, or in the system of the satellite in direction n hat, is the CMB temperature plus T_CMB times n hat dot v plus n hat dot v squared. So let's keep this term. In principle, there's higher order effects as well, but you see that this one from the measurement is about 10 to the minus 3, so this are 10 to the minus 6 effect, and so on. So it gets harder and harder to see them. So let's end it at the quadrupole for now. And then again, we're not directly measuring the temperature, but we're measuring the intensity at a given frequency. And so we can expand that. In this case, we have to expand it to 1 order higher. And so if we expand it, again, there's the constant piece that's independent of position in the sky. Then there is in our Taylor expansion di by dt, and this is just will mean that I'm evaluating it at the CMB temperature, times the temperature fluctuation. The temperature fluctuation is that thing, so it's T CMB, which is the 2.7255 Kelvin, times n hat dot V plus n hat dot V squared, and let's drop the higher order terms, and then this expansion keeps going, so there's plus 1/2 di nu d squared, so the second derivative of our intensity with respect to temperature evaluated again at the CMB temperature, and then it's delta t squared. And if we're working to second order in velocities, all we get is T CMB squared times that thing squared, n hat dot V squared, and then plus dot dot dot. So these are terms of higher order in these. And we can group these. Let's So we can group these guys. So this is I nu as a function of the position in the sky is the monopole plus, and then maybe let me leave some space here and continue here with the dipole. So let's write it as di dt evaluated at the CMB temperature times T CMB times n hat dot V, and then we write it, so there's plus and then plus, and let's again start with the second order term that has this thing in there, so di nu by dt evaluated at the CMB temperature, and then we have two contributions. So the first one is just from the line up top there, so this is I put a 1 here, and the second one I'll just write this ratio as 1 plus 1/2 f sub nu, which I'll write down in a second, times T CMB squared times n hat dot V squared, and the f nu that I'm writing here is just to get the expression there correct, is just given by d squared I nu by dt squared times T CMB, times T CMB divided by d I nu by dt. And this is a function that you can just evaluate. So if you plug everything in, the black body spectrum, you find that this is h nu over kt CMB times the hyperbolic cotangent of h nu over 2 kt CMB minus 2. So that's just what you get if you evaluate this function. And then this isn't yet quite a quadrupole. So to make it a quadrupole, what we can do is just subtract 1/3 v squared, and then we should also include the same thing up there, so plus 1/3 v squared di nu dt times 1 plus f nu times T CMB. So you see there's two effects really. So there's, on the one hand, there's a velocity dependent contribution to the monopole in the CMB maps. And then there is a contribution from the quadrupole, and what makes it interesting is that it has a different frequency dependence because of this term from the usual CMB fluctuations. So you can actually distinguish this quadrupole from an intrinsic quadrupole. So in principle, if you were to measure this term, you know that this, because of the frequency dependence, isn't an intrinsic fluctuation, which allows you to measure V, and that would then allow you to reconstruct the intrinsic CMB dipole. So in principle, you can disentangle them by going to higher orders in the velocity. What makes it a little bit anticlimactic is that this effect hasn't really been measured yet. So it's something you can in principle measure. It hasn't in practice been measured, but it's used, I mean, we assume that the motion is from the motion and then correct the maps for this. And any questions about these things? So at least in principle, it gives you a way to disentangle. And now we'll look at an effect, or look at these two effects which actually have been measured. So that will be maybe more interesting. But this is at least in principle a way you can disentangle the intrinsic dipole from the kinematic dipole by measuring the kinematic quadrupole, because it has a different frequency dependence. Okay, so now let's look at the aberration and modulation of anisotropies. And I'll stick with temperature. In principle, there's also effects on the polarization that I won't be discussing. But in principle, this is something you can also work out in the same way. So again, in the CMB rest frame, if you include small perturbations, then the occupation number now looks like 1 over e to the p over kt, which you now think is a function of the direction in which you're looking, minus 1. And so now we'll just try to convert that to the solar system frame in the same way we did before. So we'll just have to do some more Lorenz transformations. So remember that what we said is that the occupation number in the solar system frame as a function of P is equal to the occupation number in the CMB frame evaluated at lambda inverse P. So in our case now, this means this should be 1 over, and then let's write it a bit bigger so you can read it, lambda inverse P, the 0 component, this is the part we computed before, times k t, and then this should be the unit vector of the vector that you get by lambda inverse p. Let me just write it that way, and so we'll have to evaluate those guys. So again, lambda inverse we said was gamma, v gamma, gamma 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And we're working at small velocities, so we might as well expand at the beginning, not at the end. So let's write it as 1v, v1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And now we just compute lambda inverse p, and then the 0 component is the same thing we had before, and then we still need the unit vector in the direction of the vector we're getting by doing this boost. So if we compute lambda inverse p, so this is again, we're still working in the case that I'm writing here, where we're just moving in the x direction, then if we act on our p, we get p0, which is just the magnitude of p plus v times px. This is what we had before. And then here we get v times p plus px. And then here we get py. and pz. So let me just write it here to save a little bit of space. The lambda inverse p, the 0 component, is what we had before in general. So this will be p times 1 plus p hat dot v, just like we did before. And now what we need is lambda inverse p, the 3 vector. Let's write it in this way. Then this is just the 3 vector we had before, p plus the magnitude of p times the velocity, which I guess, I don't know if that helps at all, but we can also write it as p times p hat plus v. Now we need to know what the magnitude of that thing is, because we're trying to compute the unit vector in this direction. So to compute the magnitude of that vector, we just compute square root of that squared. So this is p, and then if we look at that thing, if we square it, this is 1 plus 2 times p hat dot v, but we have a square root, so the 2 goes away, and we just have 1 plus p hat dot v plus order v squared. And so if we then compute lambda inverse p hat, this is just that thing divided by this thing. The p's cancel, so we get p hat plus v divided by this is the same as 1 minus p hat dot v. And so to first order in the velocity, so here we just get p hat at order 0, then we have plus v, and then we have minus p hat times p hat dot v. And here you see that this is really just the component of v that's transverse to the momentum. So this is p hat plus what I'll call v transverse. So that's the unit vector in the lambda inverse p direction. So let's, maybe that way everyone can see it if I pull it up. Except it might be hidden behind the lower board. But okay, and so now we can plug it in. So if we write it out, what we have is that the occupation number in the solar system frame is equal to 1 over e to the, this is what we had before, so this is p times 1 plus p hat dot v. This was our dipole, and then divided by k, and t is now evaluated at p hat plus v transverse minus 1. This is again, this is in the CMB frame. And so now we can again define an effective temperature in the solar system frame or in the satellite's frame to be equal to, so there's the monopole of the CMB plus the fluctuations plus delta T in the CMB frame, P hat plus V transverse divided by 1 plus P hat dot V. And again, as before, we're not interested in an effective temperature as a function of the photon momentum, but of the direction in which we're looking. So the temperature in the direction we're looking, we're just flipping. So P hat, again, if I look in n hat direction, the momentum is the opposite of that. So I get T CMB plus delta T, again, the temperature as measured in the rest frame of the CMB, n hat minus V transpose, transverse divided by 1 minus n hat dot V. You had a question? Oh, okay. Okay, so then we can rewrite it a little bit, and then we can finally work out what the effects are. So let's write it as T solar n hat is equal to, so there's the You have a question? Oh, no. Okay, so there's T CMB plus, and then T CMB times n hat dot V, and then I have plus delta T of n hat minus V transverse times 1 plus n hat dot V. And again, I'm working at first order in the velocities, otherwise I would have the contributions that we just kept track of the quadrupole. But there isn't anything that I want to show now at the level of order V squared. So right now I'm focusing on contributions and at order V. So I have the 0th order temperature, then there's the dipole, and then there's this contribution from the anisotropies. Does that make sense? Delta T, so I'm writing the temperature in the CMB frame as the homogeneous part plus the fluctuations. So I'm saying there's small anisotropies also in the CMB frame. So those are the ones that we're trying to keep track of. And so this is delta T in the CMB frame. I just didn't put that label there. But it's supposed to be the intrinsic fluctuations in the microwave background in the frame of the cosmic microwave background. Okay, thanks. Okay, so this makes sense then? Okay, so with this, we can now compute what we find for the intensity in the n hat in any given direction. So we're doing our expansion again. So there's I nu bar the homogeneous piece, isotropic piece, plus, and then we're expanding again in the fluctuations. So there's di nu by dt at linear order, again evaluated at t equals T CMB, times the temperature fluctuation, which is T CMB times n hat dot V, plus delta T n hat minus V transverse 1 plus n hat dot V. So that's at first order, and then there's also a contribution again at, if I expand to second order, there's 1/2 the second derivative of that thing, dt squared, evaluated at the CMB temperature. And then if I square this, so I'm just squaring the delta t squared now, so if I square this, it's of second order in velocities, which I'm not keeping. If I'm squaring this, it's second order in the fluctuations, which I'm not keeping, but there's a cross term here that looks like T CMB times delta T of n hat minus V transverse times n hat dot V, and then plus dot dot dot, and because it was the cross term, the 2 is gone, so this came with a factor of 2, which cancels this one. And with this, we can now just collect the different terms again. So there's the usual, there's the monopole, I nu of n hat, so there's the monopole. Then there's the dipole plus the I nu dt T CMB n hat dot V. The dipole we worked out before, and then there's plus also the quadrupole contribution that I didn't keep track of now, but it's obviously still there. And then there are the pieces that I was interested in, so let's write them as di nu dt evaluated at the CMB temperature, and then I have this contribution here. So I have delta t, well, let me put it slightly differently. So you see that I have delta t times 1, which just comes from here. So there's, well, let's write it out. So there's the delta t of n hat minus v transverse. And then I get a factor of 1 just from here. Here I only get a contribution that involves n hat dot v. So there's a 1 plus, and then again, this is the same combination up to the factor of a half that we had earlier, where we have the second derivative of the intensity with respect to temperature times this, divided by this if I factor it out. And so I get again this function f nu times n hat dot v. And so if you look at this now, you see that there's two effects. So the first one is this one. This is the one that's referred to as the aberration. So if you're looking in the n hat direction, then you don't see the temperature fluctuation that's in the rest frame at the n hat direction, but you see, so if I'm moving in this direction, if this is v, and I'm looking in the n hat direction, then I see, if I look in the n hat direction, what I see is the fluctuation that's in the n hat minus the transverse component of the velocity to the normal is pointing this way. It's minus, so it's pointing back this way. So if I look in this direction, I see the temperature fluctuation in the CMB rest frame that's somewhat back. So the pattern is beamed. This is the aberration. You've probably seen similar examples in your special relativity class. So this is the usual relativistic aberration. And then this here is modulation effect in the sense that in the direction you're moving, the temperature fluctuations are somewhat enhanced by this amount, n hat dot v. So it's not by a whole lot because v isn't very large, but it's enhanced in the direction you're moving, and it's somewhat decreased. So the temperature fluctuations are somewhat less pronounced in the direction you're moving away from. So these are the two effects. And this one, again, the modulation has a specific frequency dependence to it. So this is something that you can look for in the maps. And this is an analysis that was done by the Planck collaboration. And they found, and it's appropriate here for the GGI, the title. So they found that the interpretation of the kinematic dipole, or the dipole as due to the motion, is consistent with this measurement, which is really a completely independent measurement. So this doesn't have to do with the dipole. This is a measurement really from the abulation, from the modulations and aberrations, and the velocity and the direction is consistent with that you would infer from just saying that the dipole is from the motion of the satellite with respect to the CMB. Okay. Any questions about these things? Okay, so if there's no questions about this, then we'll continue and look at the primary anisotropies of the cosmic microwave background. So we'll look at the primary anisotropies. And by this, I really just mean fluctuations that are intrinsic to the CMB. And not caused by the motion. Or presence of nonlinear structures along the line of sight. We'll discuss those at some later time. galaxy clusters, for example, also imprint patterns onto the cosmic microwave background radiation, but that's not included in the primary anisotropies. Those are the secondary anisotropies. So these are things that are just intrinsic to the CMB. And here, again, the way we can write it, so what we're still measuring with our instrument is the intensity in some given direction, and it'll depend on the orientation of the, you can imagine that your satellite, in addition to just measuring the intensity, can also measure the polarization. So there might be a polarization filter in front of your detector, and you might be able to rotate it. Some of the instruments work that way, many of them don't really work that way, but it's still useful to think about it that way. So you have a direction and then an angle for the polarization filter that you have on the instrument. And so here you have the monopole plus the intrinsic fluctuations, delta I nu of n hat. Again, that depends on the direction you're looking and the angle of, or the orientation of your polarization filter. And here I'm assuming now that these maps are correct for the motion. So usually the maps, if you download maps from the Planck Legacy Archive or WMAP or so on, they're corrected for the motion. So they don't have these, well, they're corrected for the dipole. They're not really corrected for modulation and aberration, but they're relatively small effects. I guess eventually when you have higher precision measurements, you should also start correcting for these, but right now they're not corrected for. So if you download the maps, you can try to reproduce the Planck analyses and try to measure the motion in this way. Okay, so the perturbation to the intensity then has a contribution that's independent of the orientation of your polarization filter. That's usually referred to as the temperature or intensity. So delta T, I'll call it, of n hat, independent of the orientation of the polarization filter. And then you have what is called Q of n hat times cosine of 2 times psi plus U of n hat of sine of 2 times psi. So you see that exactly what Q and U is depends on where you put the 0 for the orientation of your polarization filter. You also see that they then, if you rotate that, they rotate into each other. These are called, so this is the temperature fluctuation. These are called the Stokes parameters. So this is Stokes Q, and this is Stokes U. And in principle, that's all that you have to know. Maybe let me briefly say that often, if you look at the literature, often you may find that this is written in terms of an intensity matrix. And the intensity matrix is defined so that the intensity of n hat and psi is equal to the intensity matrix ij of, which is now only a function of n hat but not psi, contracted with polarization vectors. So I, which is a function of psi, and ej, which is a function of psi. So these are polarization vectors that characterize the state of the detector. And this thing here then just characterizes the radiation field. So the nice thing about it, I guess, is that you're describing the characterization, the radiation field in a way that's independent of the detector. And I won't use it much, but maybe let me just write out the intensity matrix if you're looking in the z direction to give you an idea. So if we're looking up in the z direction, then this intensity matrix z hat ij would be on the diagonal. You have delta q, in this case of z hat, so let me not always put the argument, it's just the temperature fluctuation in that direction, plus q. Then you have u plus iv 0, u minus iv, delta t minus q 0, 0, 0, 0. And then you see that the trace of the intensity matrix is related to the temperature perturbation, and then the Stokes q and u parameters are components of a symmetric 2 tensor on the 2 sphere, and there's an additional guy which is Stokes v, which is not usually discussed much because it corresponds to a circular polarization. Circular. Spider recently provided limits on the Stokes V parameter, but usually it's not reported. So usually what you see are the Stokes, the temperature fluctuations and the Stokes Q and U parameters. Also, if you download the Planck data, this is the way the data comes. So there's usually 3 fields. Here I'm just showing you 2 of them. So there's, if you download it, there's a temperature map, which looks like this, and then there's a Stokes Q parameter and a Stokes U parameter. So you have 3 fields when you download them, and it's these guys. So it tells you then what the radiation looks like. And I didn't put Stokes U just because I didn't have space. But if you download the files and play with the maps, this is really what it looks like. And if anyone is interested, I'm happy to play with if anyone wants to download and play with it, I'm happy to provide some help. Okay, so these maps, this is how the data is stored, but it's not something that we can directly predict. We can't predict that a given spot in the sky is going to be hotter and another spot is going to be colder. So we can't really directly predict T, Q, and U. We can only predict the statistical properties of these guys, of T, Q, U. And so by that I mean we can compute correlation functions, let's call it delta T. So we can compute correlation functions between the temperature fluctuation in one point on the sphere and some other point on the sphere, or correlations between delta T of n hat and Q plus minus IU. The reason to write this combination is just that it has nice transformation properties under rotations. It transforms by e to the 2I times the rotation angle. And then similarly, you can look at correlations between Q plus minus IU and Q plus minus IU. And so in principle, this is something one could do. And if you look at the first set of papers, or the old papers by Kobe, then they report the temperature correlation function. So they really report this quantity. And since then, that hasn't really been done. So the reason it's not usually used is that the covariance matrices of these don't have very good properties. So they're not diagonal in any way as a function of the angle. So there's correlations, and the plots are kind of hard to interpret. So it's not something that's used. So instead of working with the with the maps of T, Q, and U. Instead, we work with what are called multiple coefficients. So the multiple coefficients are just defined in the usual way. So you have ALM of T. You can define it as integral over the sphere of delta T against a spherical harmonic, or in other words, these are the you can expand the temperature fluctuations, which are a function on the two-sphere instead of in terms of spherical harmonics. So this is the integral over the sphere. And let's look at the reality properties. So if you complex conjugate the thing, ALM T star, this is equal to the only thing, the temperature field is real, so the only thing that happens is that now you get YLM of n hat. And so what we would like to know is how the complex conjugate of spherical harmonic is related to the original spherical harmonic. And you've probably seen these relations many times in quantum mechanics or in other places. The conventions that are used in this context in the textbooks usually are slightly different from the conventions in quantum mechanics. Well, also some older quantum mechanics books use these same conventions. But so this is just a convention, is that YLM star of n hat is YL of minus m. In quantum mechanics, I'm used to the Condon-Shortley phase, which gives you another factor of -1 to the m here. But in any case, this is the one that's usually used here, which also means that if you complex conjugate this, you get this guy. So in these conventions, this is YL minus m star of n hat. And so then in these conventions, you see that you just get A, T, L, M complex conjugated is the same as A, L minus M of T. This is the consequence of the temperature field being real. And then we can introduce similar multiple coefficients for the polarization. And here, what's usually introduced is initially is called APLM, which is essentially the same, except that the Q and U, as you can see here, so the T is really a function, or if you want a section of the normal bundle, or just a function. These are components of a symmetric 2 tensor. Or if you write it, the reason I was writing Q plus IU is because you can write the Q plus IU, you can think of as a section of a complex line bundle over the sphere. So then it means that you shouldn't be expanding in terms of the eigenfunctions of the Laplacian on the space of functions, but the Laplacian on the space of these sections, which are the spin 2 spherical harmonics. So that's the only slight difference. But conceptually, it's the same thing. So you're just expanding them in terms of some special functions and get the coefficients. And now, because this thing isn't real, this guy doesn't have nice reality properties. So usually, we then define some quantities that do. So you define something like a real and imaginary part of this thing is AELM is -1/2 A P L M plus A star P, well, let me keep it up here. So the AL minus M, and then similarly, you can define AB LM, which are equal to minus 1 over 2I A P LM minus A star P L minus M. And this definition is also convenient because they have nice transformation properties under parity. That's one of the reasons to really introduce them. And under parity, they transform in the following way. So under parity, so x goes to minus x, you just get that A, L, M, E goes to minus 1 to the L, A, L, M, E, and AB, LM goes to minus of that, minus 1 to the L, AB, LM. And this transformation property is also responsible for the name. So this roughly transforms like an E field. This roughly transforms like a B field. It's not really quite true because these aren't vectors. They really spin two objects, but this is in any case the analogy that gives them the name of E and B modes. Okay, so these are the multiple coefficients for temperature and polarization. It's just notation, really, just conventions. And then just to see that you get the same things as you would get from the correlation functions, let's look at what you get if you compute the correlation function between the temperature at n hat and the temperature at n hat prime. So here then we have sum over L and M for the first guy, L prime, M prime for the second guy. Then we still have our ensemble average. The first one is, let's call it AT LM. And then the second one, without loss of generality, I can call it A star as long as I keep track of what I'm doing with the spherical harmonics, L prime, M prime. And then this one here I should write as YLM of n hat without the star. The other one should have L prime, M prime star of n hat prime. And then by rotational invariance, so the whichever one, yeah, anyway. So by rotational invariance, this thing just has to be some function which can only depend on L times delta LL prime times delta M prime, and this is because it's TT, it's called the temperature power spectrum, and this is called the angular power spectrum. And so then if you plug it in, you find that delta T of n hat, delta T of n hat prime is equal to, so this thing just cancels these sums, so we still have a sum over M. So we have a sum over L and M. This is just CL TT, and then we have the spherical harmonics, YLM of n hat, YLM star of n hat prime, and then for everyone who likes spherical harmonics, you'll recognize that the sum over M is something you can still do and write this in terms of a Legendre polynomial. So there's a 2L plus 1 over 4 pi times PL of n hat dot n hat prime times CLTT. And so you see that it really only is a function of the angle between the two vectors, which it had to be by rotational invariance. And you also see that there's a one-to-one correspondence because these are orthogonal polynomials. You also see that there's a one-to-one correspondence between the CL and the correlation function. So once you give the correlation function, you have the CLs and the other way around. So all the information, at least for Gaussian fluctuations, the information that's contained in the correlation function, in the correlation functions, is contained in the angular power spectra. So these are A, T, L, M, A star, T, L prime, M prime, the ensemble average. This one we were calling TT, delta L, L prime, delta M, M prime. And then similarly, you can do it for the various other spectra. So there's A, L, M, T, A star, E, L prime, M prime. This is equal to CL. This is called the TE cross spectrum, delta LL prime, delta MM prime. And then finally, there's two more auto spectra, A, E, LM, A, E star, L prime, M prime. This is equal to CL. This is the E mode auto spectrum, delta L, L prime, delta M, M prime, and A, B, LM, A, B star, L prime, M prime is equal to CL, BB, delta LL prime, delta M, M prime. And then if you assume that your theory respects parity, or if your theory respects parity, then this is all there is, because C, TB, and C, EB are 0 if your theory respects parity. And you can see this right away from the transformation properties that I just erased. So under parity, you get a -1 to the L for -1 to the L for B, and -1 to the L for T and E. So whenever there's a single B, you just it goes to minus itself, which means it has to vanish. Okay, so we're almost there and can look at the data. I want to make one more comment, which is just that these are the ensemble averages that I've been writing, meaning we're averaging over many realizations or many different universes. That's what we mean. So we have one underlying theory, and we predict a bunch of different realizations, and this is the underlying CLs. But in practice, we only have a single universe to observe. And that means that what we're measuring has to be somehow built of the ALMs for a given map, so we can't compute these ensemble averages over different realizations. So we're writing the estimator A TT of L as 1 over 2L plus 1 sum over M of ALM squared. So this is the average over these guys, and this is the observed ones now. And so if you take the ensemble average of this thing, so if you in every realization you measure this thing and you ask how it's related to the underlying theory CLs, so if you compute this, CL, TT, the ensemble average, this is 1 over 2L plus 1, but then the ensemble average of this is just CL, TT, so this is sum over M, CL, TT. There's 2L plus 1 of these guys, so this is just CL, TT. So this is an unbiased estimator on a given sky. But, and I won't derive it, it's easy, it's something you can do as an exercise basically from these definitions and just Wick's theorem, or the property that for Gaussian fluctuations, if you have higher order correlation functions, it's the sum of products of the 2-point functions. then you can show that CL minus CL hat squared, if you compute this, so that thing doesn't average to 0. This fluctuates around the true value by an amount that's set to by 2 over 2L plus 1. So the more modes you have, the less the fluctuations away from the true value times CL. But it means there's some fundamental limitation to how well you can actually measure the underlying, well, let's put this is a general statement, so let me not put the labels. So it's delta CL. There's some underlying limitation of how well you can measure them, which is just given by this is squared, sorry, CL. And this is called cosmic variance, this phenomenon that we cannot measure them arbitrarily well. Okay, and so now all that said, we can look at the measurements again from the data. And again, I wanted to start with the old measurements. So the first claim of measurement of the anisotropies, so in this case, measurement of the anisotropies of the quadrupole, so C sub 2, was claimed in a reanalysis of relict 1. So relict 1, usually relict 1 isn't all that well known, but that was a CMB satellite that was launched by the Russians before COBE. And so there's a claim in there. Usually it's forgotten for presumably also because it's at a single frequency, but also because even relict typically is kind of ignored when people talk about CMB satellites. But so there was a claim in this reanalysis, and then the measurement that's usually credited with the detection of the anisotropies in the cosmic microwave background is COBE, and in particular the DMR instrument. We saw the detector earlier in the picture that I had from George Smoot, where it was on the spy plane. So it's the same detectors that flew on COBE DMR and provided this map of the anisotropies of the cosmic microwave background. So in this case, it's measured at 3 frequencies, 31, 53, and 90 gigahertz. And so there you can really disentangle and figure out if what you're looking at is really in the cosmic microwave background or it's galactic. And so in that sense, this is certainly much more convincing. And then as time goes on, more and more measurements came around. So there is the measurement here, the black points here are the measurements from the COBE satellite. And then the rest essentially ground-based and balloon experiments. So there's Matt, Toko, Saskatoon are starting to see what we now know is the first acoustic peak. Usually the instrument that's credited with detecting the first or the acoustic peak is Boomerang and Maxima, and here is their data, so from 2001. So you see that it's improving relatively quickly. So this is then the measurement by WMAP, which you might have seen. Here the gray band is what I just discussed. So this is this cosmic variance. This is a band that's just indicating cosmic variance by how much you might expect these to fluctuate, just because we're looking at one single realization and can't calculate any ensemble averages. And then toward the end where you see the error bars go up, this is instrumental. So the cosmic variance there is very small because L is large, but there the instrumental noise gets large. Here I'm also showing the measurement of the TE cross spectrum, which is this guy here, the TE cross spectrum from the WMAP satellite. And finally, now what it looks like is that we have the Planck TT spectrum, and here you see that now the TT spectrum is extremely well measured out to L of about 2000 or so. So in this case, the green band is the cosmic variance limit. The gray dots are the individual multipoles. The blue data is spin, so there's no indication of how big the cosmic variance there is. But the noise here is much smaller than the cosmic variance. The noise starts to take over only above 1800 or so. So you see here when the band increases, this is from the instrumental noise. So out to L of 2000 or so, the temperature fluctuations are now very well measured by the Planck satellite. And so the next question will be, what is the physics underlying this? I mean, how is the red curve made? How do you actually compare theory and experiment? And how do you understand what the underlying physics is? So that's what the next goal for us is, to understand that. Okay, so let's start with that. So I still have time. Before I start, maybe just everything clear about the various definitions. Any questions about the last part? No? Yeah? Yeah, I mean, there are some ways of writing raising and lowering operators. There's also a way to get them from the representation of the rotation group. So if there's a way to think of the ordinary spherical harmonics as the rotation group with one of the as a representation of the rotations with spin L. So you can write D, let's call it D sub L, as a function of the rotation that takes you from the 3 direction to the n hat direction. So there's some standard rotation you can define to go from the 3 direction to the n hat direction. And then you can define here m prime. And then if you set m equals 0, you get the usual spherical harmonics. If you set it equal to 2, you get the spin 2 weighted spherical harmonics. So if you wish, that's one simple way of thinking about them. There's also differential operators that you can use as raising, lowering operators. So they're closely related to them. Any other questions? Yeah? The Milky Way in the measurement, what you do is you cut it out. So you have some mask that downweights the pixels where you think you have a contamination. So this is true for the Milky Way. It's also true for point sources. So there's a lot of point sources in the sky, in the microwave sky, so you mask them. And in principle, this should be included in the estimator that I was writing here. I didn't include it, but when I'm writing an estimator, CL hat TT, and I'm saying that I take 1 over 2L plus 1, sum over M, and then A, T, LM, absolute value squared, where these ALMs are just the versions that I get from finding the delta. Then that's not going to be good if there's a galaxy in the way. That's what you're asking, right? And so usually what is done is that you actually mask the sky. So you have a temperature map, and then what you do is you multiply this by some weights, n hat times delta t hat, and let's call this, I don't know, some other number, some other thing. Let's call it delta tilde. And then what you do is you compute some A tilde TLM of these guys. You can compute some CL tilde TT from these guys in the usual way. So these are still 1 over 2L plus 1, sum over M, A, LM tilde squared. And then the question is, how are these tilted C's related to the underlying CLs that you're trying to estimate? And if you want, we can go through it in more detail, but eventually you can work it out analytically how this works, and there's a relation that relates, at least on average, so if you take the ensemble average, CL tilde TT, then this is related to the other ones by some what is called the mode coupling matrix, so sum over L prime of the true CLs that you're interested in. And so when you're trying to estimate these, what you want to do is invert the mode coupling matrix. So the estimator you usually write, L is something like the inverse of the mode coupling matrix LL prime C tilde TT L prime. So this is kind of what you're doing, where this is this guy for the masked map. And if you mask it too badly, then this mode coupling matrix isn't invertible anymore. So roughly this is only invertible if you can really measure the correlation function over all scales still. So if you make a very small patch of the sky, for example, shouldn't be surprising that you can't invert it, because you can't measure the lowest scales. You can't measure L of 4 if you only have a small patch in the sky. So eventually then you have to start binning the data. So if you see that the data is binned in L for the experiments with small sky fraction, then this is because the mode coupling matrix as it is isn't invertible, and you have to do something to invert that, and you're measuring band powers instead. But for the Planck maps, this is really what's done. So you basically downweight the pixels that you don't like. So usually there's a mask for the galaxy, mask for point sources, and then you just undo that masking later on. Does that make sense? Okay. Any other questions? Yes, I skipped over that a little bit, but. Okay, so then let's start with the calculation of the angular power spectra. And so for this calculation, just like the calculation of the spectrum, typically, at least conceptually, it's useful to think about the universe at a temperature of just below 10 to the 9 Kelvin, or again after E plus E minus annihilation. And so in that case, we know that the universe is filled with photons, electrons, protons. So there's many fewer of these than the photons, because we're at high temperature in the radiation-dominated era, where these carry there's always many more of those, but they also carry the energy density. Then maybe helium, deuterium. Then there is dark matter, and there's neutrinos around. And so in principle, or in practice, when people analyze it, what's done is relatively, it's conceptually straightforward. So you write down the kinetic equations for that system. So the Boltzmann equation, including collision terms and so on. Then you linearize you solve that system of equations numerically, and compare with the data. Obviously, if that were what I'm discussing now, it's a little bit anticlimactic. So what we'll try to do now is to not start with the full system, but again to consider a toy system, toy model, so we get some analytic understanding of what the underlying physics is, and then we can generalize to the full system, hopefully fairly easily. So we'll consider a toy system where, so what I'm trying to show you for now is essentially where the peak structure comes from. And for this, what we can ignore for a second, this is coming from what are called the fast modes, or the baryon acoustic oscillations. So for now, we'll ignore the neutrinos and the dark matter. Obviously, eventually we have to put them back in, because the dark matter is responsible for creating the potential wells that set how large the amplitude of the fluctuation is, and so on. It plays an important role, and it's detected at something like 80 to 100 sigma, depending on exactly what you're doing. So it's clear that we have to eventually put it back. But for now, let's take out the dark matter. We're also going to ignore gravity. And we'll make it even simpler and ignore the photon and spins. And at least for now, let's think again in the simple framework that we had before, where we think of a tightly coupled phase followed by instantaneous last scattering and then free streaming. So we consider okay, so that's the toy model we'll consider. And so then the question is, how do we describe our photons? And the goal here is, at some level, to understand the underlying physics, but at some level also to introduce the notation that's used in if you eventually then look at the papers or try to read the codes, so you know what the different symbols are, because there's a lot of notation that's floating around. So there will be a fair amount of notation introduced. So hopefully you can follow along the steps, because that's the point of what I'm doing now. So if there's a step that you're kind of missing, just ask again, because the point is really for you to be familiar with the notation and also see what the physics is, but also to a large extent to understand the notation. So I'll use the same notation that I'll use later on. So we describe the photons in terms of, or by their phase-space density. Which I'll write as n of x, p, and t. And here the idea is that the number that this gadget, n of x, p, and t, the phase-space density times integral, or times d3x, d3p, is the number of photons in a volume d3x, d3p in phase space centered at xp. So it just tells you how many photons there are at x with a given momentum. And so the first thing we should figure out is what is the equation of motion for that. And in our description, there will be two different versions. So we will have a tightly coupled early phase where the photons and electrons are scattering. And then we have a free streaming phase. And because this one is here, we'll start with this one. So we'll work out what the free streaming phase looks like first. We'll start with 2 and ask what is the equation of motion for the phase space density, and a useful way to think about the phase space density, which makes sense as long as the photons, the number of photons is conserved, is we can think of the phase space density as sum over r delta of x minus xr of t delta of p minus PR of t, where here I'm summing over all the photons in the system. So I'm just putting a delta, so this is just a 6-dimensional delta function in phase space. So if I integrate over the little volume, it just counts the number of photons in that volume. So this sum runs over the photons in the system. And so then I can calculate d by dt of that thing. So d by dt of the phase space density is equal to, and so first it acts on this piece, so there's a time dependence because the thing moves, and then there's a time dependence because the momentum might change. So when it acts here, so it's d by dxr times xr dot. Instead of taking the derivative with respect to xr, I can take the derivative with respect to x if I put a minus sign in there. So I can write it like this, sum over r and then xr dot I d by dxi of this thing here, dx minus xr of t delta of p minus pr of t. And then the second contribution is when it acts here, which works in the same way. So this is d by d, the partial derivative with respect to PR times PR dot. Instead of taking the derivative with respect to PR, I can again take the derivative with respect to P if I include a minus sign. So there's minus sum over R, P, R. Let me put the index down for no very good reason at this point, but it's more convenient in general relativity to write it that way, because then this thing is invariant under coordinate transformations. D by d p I delta of x minus xr of t delta p minus pr of t. And then this here, for a photon, it moves at the speed of light. So this is just a unit vector in the direction of the momentum of the photon. So this is just PR hat the I component. And because of this delta function, this is also the same as P hat I. So then you can pull out this whole differential operator. And here, if we're in the free streaming phase, the momentum of the individual photons doesn't change. So this thing is equal to 0. This will eventually change in general relativity if you have a photon that's in a gravitational field, because then it follows a geodesic in space-time. And so then here you get the contribution from the geodesic equation because the momenta do change. But for now, it's just 0. And so the equation of motion for the phase space density, so then this piece is 0 altogether. This differential operator we can pull out. And so if we pull it out, we just get dN by dt is equal to minus p hat dot the gradient times the phase space density. So this is the, if we bring it to the other side, we just see that this phase space density obeys a collisionless Boltzmann equation that looks like this, dot grad n of x, p, and t is equal to 0. And what we're interested in is a scenario where the phase space density is essentially close to homogeneous and isotropic with small fluctuations, and the piece that's homogeneous and isotropic is again the black body function. So this is true for a general radiation field or massless particles, but for now we're interested in a scenario where it looks like n bar of p, which is our black body function, plus delta n of x, p, and t. And so the Planck spectrum just obeys this, so it doesn't change either as a function of time, and there's no gradient. So this part just goes away, and we see that also the perturbation to the phase space density obeys the same equation. Delta n by dt plus p hat dot the gradient times delta n of x, p, and t is equal 0. So far so good. Now we'll try to relate this to quantities that we actually care about, because these are the quantities we measure. So we'll try to relate this to what a detector actually registers. And so if you have this phase space density, it tells you at any given point how many photons are coming with what momentum. So if you have a detector that only accepts photons with momentum in the p hat direction, but is ideal in the sense that it's taking or measuring sensitive to photons of arbitrary energies, which isn't in practice isn't the case, but for now let's work with that. And it's equally sensitive to all of them. It just really measures their energy. Then the response of that detector will be proportional to integral and then p cubed dp over 2 pi squared of delta n of, if you put the detector at position x, p hat, and it registers only photons coming from the p hat direction, so you have infinite resolution, which also isn't necessarily the case. So usually there's then some a beam convolution, and in practice usually here there's a band pass, so it's not really equally sensitive to photons of arbitrary frequency, but in our idealized case we can write the response that's proportional to this. And so that suggests that it's useful to introduce a variable that looks like this. So delta t, which is a function of x, of p hat, and t, which is equal to the thing I just wrote, p cubed dp over 2 pi squared delta n of x, p times p hat, and t divided just by the background density or the energy density. So integral d3p over 2 pi cubed times the energy of the photon times the background value. So this registers the temperature fluctuations, as we'll see. So to understand that a little bit better, or to understand this quantity a little bit better, let's first see what happens if you average it over all directions. So if you average it over direction, so you take integral d2p hat over 4 pi of delta x p hat and t, then you see that this just becomes the same kind of integral with a p. So this eventually just becomes delta rho of x divided by rho bar. And because the energy density goes like the temperature to the 4th power, this is also 4 times delta T of at the position x divided by T bar. And similarly, if you're just looking at this thing at the origin, let's say, or at any position, and you're looking in the p hat direction or minus n hat, so if you're looking at the n hat direction, it's registering photons with momenta with a direction minus n hat of t. This is just equal to 4 times delta t, the temperature fluctuation in the n hat direction, divided by T bar. And if you look at how this quantity is built from the density, from the perturbation of the phase space density, you see that it will obey the same equation. So this quantity still obeys d by dt delta t of x and p hat and t plus p hat dot the gradient of delta t of x, p hat and t is equal to 0. And now I'm not sure exactly what I should do about the time. Do I stop? Okay. So let's just stop here and then continue. But we'll massage this this quantity further. So eventually, we're almost at the quantities that are actually used. So okay, so we'll continue next lecture, I guess.